Hello everyone, in this video I will explain you the basics of model reference adaptive control, and moreover I will explain you how to implement a simple model reference adaptive control algorithm in Matlab. Everything that I will explain in this video can be generalized to more complex systems and to more complex model reference adaptive control algorithms. Okay, so let's start. This is the post I created that thoroughly explains the model reference adaptive control algorithm. But before I start, I need to explain why I created this video. Well, the motivation for creating this post comes from the fact that Matlab implementation of model reference adaptive controllers is usually omitted in control theory books. However, implementation is far from trivial, and there are a number of pitfalls that could potentially lead us to misleading conclusions. So consequently, I wanted to clarify how to implement a model reference adaptive control algorithm in Matlab, since this is a very important topic that's often being overlooked by people who are teaching control theory. Okay, so let's start. We are basically focusing on a simple first-order system represented by this differential equation. So this is our plant that we want to control. Y is the output of the plant, A is the parameter, and B is the parameter. And we are assuming that we know the structure of this plant. We know that can be approximated by a first-order differential equation. However, we assume that we don't know the constants A and B. Now, the goal of the model reference adaptive controller, MRAC, is to compute a control input such that the system output is as close as possible to an output of a reference model. Now, what is a reference model? The reference model is the model that specifies the desired system behavior. That is, the output of the reference model is the desired system output that we want to achieve in practice. And this is a general form of a reference or a desired system model, and we want our model, our plant actually, to behave in a similar way to the behavior of our reference model. That is, we want this output ym to be as close as possible to y, or the other way around, we want y to be as close as possible to ym, and we want to find a control law, u as a function of time, that will achieve that. Let us analyze the reference model. Ym is the output of the reference model, uc is the input of the reference model, and AM and BM are the model parameters that are known, since this is our reference model that specifies the desired system behavior. We assume that we know these parameters because we designed them. Now, the signal UC is known. It can be a step signal, it can be a pulse train, it can be a sinusoidal signal. Now, since UC is known, we can simulate the reference model, basically solve this ordinary differential equation to compute ym as a function of time. So ym is known also. And we want to make sure that our plant or its output y follows this signal. Now, the control input structure that achieves this has the following form. We see that the controller itself takes the input to the reference model, it takes the output from the plant, so this is the feedback mechanism, so the control signal takes the output from the plant, and these parameters θ1 and θ2 are the parameters that we want to design. So we want to specify these parameters, we want to find these functions θ1 and θ2 as functions of time. So we want to find θ1 as a function of time and θ2 as a function of time. Let us summarize the control objective once more. The goal of the adaptive control algorithm is to determine the parameters theta 1 of time and theta 2 of time, such that the system output y of t is as close as possible to the output of the reference model ym of t for some selected reference input function uc of t. So let us see how to achieve this control objective. Well, the first step that you need to take is to substitute this control algorithm in the system dynamics. So if we substitute the equation 3 in the equation 1, at the end we will obtain the closed loop system 4. Now, let us analyze and compare the closed loop system 4 with the equation 2 that specifies our reference model. What do we see here immediately? We see that if our theta 2 and theta 1 are selected as the forms given in equation 5, we will see that basically this term over here becomes am and this term over here becomes bm. That is, we achieve the desired system behavior. However, the catch here is that we cannot determine the parameters theta 1 and theta 2 in this way, since we don't know a priori the system parameters a and b, right? The plant parameters are unknown. The plant dynamics is unknown. We only know the structure of the plant dynamics. Nevertheless, the values of the parameters theta 1 and theta 2 that achieve the most optimal system behavior are important for us, since we can verify our simulation results. If our control algorithm is designed in a proper way, our parameters theta 1 and theta 2 should converge to these values in our simulations. Okay, now the next step is to derive the algorithm. So there are many ways of deriving the adaptive control algorithm. We're going to use the so-called MIT rule. So what is an MIT rule? Loosely speaking, the MIT adaptive control rule aims at minimizing the following cost function. So we take the error, we square the error, and we are trying to minimize this cost function, where the error is simply the difference between the output of the plant and the output of our reference model. Now, to decrease the value of j of our cost function, it's reasonable to adjust the parameters theta 1 and theta 2 in the direction of the negative gradient of j. That is, we can simply state that the change of theta 1 and change of theta 2 in time should be in the negative direction of the gradient of the function j with respect to the parameters theta 1 and theta 2. And now if you compute these partial derivatives, you will obtain the equation 8. Now let us work around and let us try to find these partial derivatives. The first step is to introduce the differential operator. This is a very important operator. So we can represent the derivatives as p times f of t. This is very similar to the Laplace approach, where the complex variable s has an interpretation of taking the first derivative. Consequently, from equation 4, and equation 4, if you look back, specifies our plant dynamics, we can simply represent this first derivative as p times y, right? And by working these expressions and a little bit doing massaging them, that's what we like to say in control engineering terms, we like to massage the equations. From this equation we obtain the output, and if we substitute this output of the plant into the system dynamics, we obtain the error. So the error is given by the equation 11. Now we can simply take the partial derivatives of e with respect to the parameters theta 1 and theta 2, and we obtain the expression 12. So the expression 12 represents the partial derivatives. Now let us analyze these partial derivatives. Are they computable? Well, they are not. And the problem is that the parameter a and b are unknown, right? We don't know the plant dynamics. So we need to introduce some approximation. Now, In ideal scenario, the parameters theta1 and theta2 should converge to the values theta1 star and theta2 stars that render the closed loop dynamics to be equal to the reference model dynamics. Well, if you go back, so if theta1 is equal to theta1 star, bm over b, and theta2 is equal to theta2 star equal to am minus a over b, then we know that we have a perfect or the most optimal controller. Well, from this equation, from the equation 5, we can use equation 5 to assume the following. We can assume that basically the parameters theta2 are very close to the theta2 star, and this renders this whole term am to be equal a plus b theta 2 star, and this is approximately equal a plus b theta, right? And using this approximation, we can approximate these two terms in the denominator. And basically, our partial derivatives become p plus am in the denominator, right? So the dE over d theta 1 becomes buc over p plus am. Now, but here is another problem. We still don't know b. Well, we can get rid of b. We can basically group it together with the control gain. And this is explained in the equation 16. Basically, by substituting the equation 15 in the equation 8, we obtain the equation 16. Now, what can we do with this equation 16? Well, we can regroup the parameters and add additional parameters over here. Actually, we are not adding, we are just multiplying the equations by am over am. And what do we obtain? We obtain this term over here and this term over here. And now we can call this term gamma. This will be our control gain. That's adjustable parameter in the adaptive control algorithm. And the final expression for d theta 1 becomes minus gamma am times uc over p plus am times error. Now, everything here is computable if we specify gamma, and we can freely choose gamma. You will see later on in Matlab simulations how does the parameter gamma influence the system dynamics. We do the similar trick with d theta 2 over dt, and we obtain the final expression given by this equation. And as I said previously, alpha times b over am is a new control gain. Now, one important thing has to be mentioned here. We have normalized the control gains. We have normalized the control gains in this way, basically, or actually not the control gains. We have normalized this filter 1 over p plus am, and it becomes am over p plus am. In this way, we achieve a steady state gain of 1, which is very convenient for a control algorithm. The equation 16 is very important since it specifies the change of the parameters theta 1 and theta 2 with respect to time. We see that theta 1 and theta 2 are the functions of error, control gain, system output, and the input to the reference model. And plus we have these filters over here. These equations in the equation 16 should be coupled with equation 10. Right? The equation 10, its form over here, describes the plant's dynamics. So equation 16 and 10 specify the dynamics of the closed loop systems. These equations are written in the mixed time domain and differential operator P forms. So in order to simulate these two equations, we need to convert them to a pure time domain, and we need to write a state space model. So after a few algebraic steps, mainly, we want to get rid of these P differential operators here and here and here, and the equation 10. We can simply do that by revoking the definition of differential operator, and at the end we will obtain the state space model. Actually, it's not a state space model, this is still a system of three differential equations, and we need to write these differential equations in state space form. How to do that? Well, we can simply introduce the state space variables. x1 is θ1, x2 is θ1 dot, x3 is θ2, x4 is θ2 dot, and x5 is the output y. Now, you might ask me, how about ym, and uc? What happens with these variables? Well, these variables are known functions of time because we can simulate the dynamics of a reference model for known value of uc, and we can obtain ym. So they act as inputs, they drive this model. So at the end, you can see over here that our original system that was of first order becomes a fifth order state space model when we couple it with adaptive controller. So this is a price that we need to pay for an adaptive controller. We increase the system order. And moreover, you can observe that this is a nonlinear state space model, right? Although the dynamics is linear, when we couple dynamics with the adaptive controller, the system becomes nonlinear. That's why you should study nonlinear control systems. Okay, so this is our state space model, and let us simulate its behavior. So I'm just taking one of the examples from this book, from a famous reference on adaptive control by these two very well-known authors. And the example number is 5.2. So I'm taking the 5.2 example, I'm taking the same variables, and I'm simulating the system dynamics. And so here is the Matlab code for simulating the system dynamics, and in the sequel I will explain this Matlab code. Before I start, I have to mention that all the codes in this video will be posted on my GitHub page. A link to my GitHub page is given in the description below. So let's start. First, we need to specify the reference model parameters, the planned parameters, and we can simply compute the final values of the parameters for verification of the convergence of our adaptive control algorithm, right? Then we specify the reference model by simply typing a transfer function, bm, in the numerator and 1 plus am in the denominator. So this is our planned, right? Then we specify the maximum or the maximal simulation time. We specify the time vector, and we define a reference input signal, which in our case will be a pulse signal. So let's see how does our input signal look like. So this is our input signal. This is an input to the reference model. And let us simulate the reference model or our desired system for this input. We can do that by simply using the Matlab function lsim. We specify the transfer function, we specify the input, and we specify time vector. Let's see what happens. Okay, so let us analyze the results. This red line is the output of the reference model, and the blue line, or actually the black line, is the input to the reference model. That is, again, red line, the output of the reference model, and the dark or the black line is the driving input. We can see that after some transients, the output follows the input. This is because the system is stable. Okay, so let's continue. The next step is, of course, to simulate the system dynamics, the closed loop system dynamics, and to simulate the adaptive controller. To do so, we need to specify basically the function that defines the closed loop dynamics. So I'm going to open this function. Here's our function. It's called dynamics adaptive. This function takes time and x as inputs. T is a scalar, x is a 5 times 1 vector, is the vector representing the time series of the reference model inputs, ym is a vector representing time series of the output of the reference model. So these two variables are known and act as inputs. This is the time vector for simulation. AM, BM, A and B are actually parameters, and gamma is the control gain. Now here's the trick. So since OD45 cannot accept time-varying inputs or time-varying parameters, we need to do the following trick. So we're going to interpolate from and from ym the values specified at certain times t. So we are going to use this trick. I have created a complete video that explains how to do that, and you can read more about this video and this approach in the post that I previously explained. And here's our dynamics. So this is dynamics of our system. And if you go back here, so these are the state space variables. And let us compare. So x1 dot is equal to x2. So let us go back to our code, and we can see here dx dt 1 is x2. This is the first equation. This is the second equation, the equation over here, and etc. Third, fourth, and this is the fifth equation that you can see over here. Now, we're basically now ready to simulate the system dynamics. So first we specify the initial condition, zeros, although you can also specify arbitrary system conditions, and you can specify the gain gamma. In our case, we are going to select gamma 0.5 and we want to see how does the system behave for this parameter gamma 2 equal to 0.5. You can change it to any value. You might obtain maybe unstable behavior, watch out. So let us do that. So we simulate the system dynamics. It's going to take a while. Although I'm having a new computer, we still need few seconds to simulate the system behavior. And let us extract the state space variables, because the state trajectories, the output of this simulation, contains a matrix basically that has 5 columns, and the number of rows is equal to the number of samples in the time vector. And let us plot the system response. So first we are going to plot the output of our reference model and the output of our plant. The purple line is the output of our plant, and the dark line or the black line is the output of the reference model. So the purple line should follow the black line. We see that the tracking performance is not bad, however it's not perfect, and the reason is that this parameter is relatively small. We can increase this parameter to obtain a better tracking performance. And finally, we can plot the trajectories of the parameters θ1 and θ2. The dark line, the black line, is θ2, and basically the purple line is the parameter θ1. And the desired values are basically, not desired, the most optimal values are basically 4 and 2. And by observing these transients, we see that basically θ1 and θ2 are kind of approaching these parameters. We didn't simulate the dynamics for more than 100 seconds. However, we can do that, and you can observe that they will converge, these parameters will converge to the most optimal values. So let's see what happens when we increase the parameter values. And I'm going to go back to the post, since I've generated the simulation results. This is the first graph you have seen, right? This is the second one. This is basically the comparison of the reference output and the controlled output of the plant for gamma equal to 0.5. And this is the parameter convergence for basically θ theta for gamma 0.5, you can see theta 1 and theta 2. Okay, so let's see what happens when we increase gamma to 2. Well, we see a dramatic change. First of all, we can observe that the tracking performance after, let's say, 50 seconds is almost perfect. However, the price we need to pay is basically increase in overshoot, right? We see more overshoots over here. Now, let us try to be more aggressive, and let's try to basically increase gamma to 4. And this is what happens when gamma is increased to 4. So the figure 6 represents the case when gamma is equal to 4, and we can see almost perfect tracking after 20 seconds. However, you can see these overshoots that are signs of instability, of the system instability. And you can see the parameter convergence. Basically, theta 1 converges after, for example, 40 seconds to an almost 4, which is basically the optimal value of theta 1, and theta 2 converges also after 40 seconds to the value of 2, which is an optimal value of the control parameters. Now, you can also simulate the system behavior for different initial conditions, for different values of gamma. However, in this video, I have explained you the general principles for simulating the closed-loop adaptive controller. Now, that would be all for today. I hope that you like this video. If you find this video useful, please subscribe or support my channel. Thank you very much and have a nice day.